Oh, level 3. So the integers 1 to 64 are written in the squares of an 8 by 8 chessboard, such that for each I between 1 and 63, the numbers I and I plus 1 are in squares that share an edge. And so we want to find the largest possible sum that can appear along one of the diagonals. And so first of all, clearly the maximum sum will appear along one of the two diagonals of length 8. And so you can claim that the maximum sum is simply in this grid that I'm about to draw. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, and 64. And so the diagonal that we're going to consider is the one made of the squares highlighted in yellow. Okay, so the maximal sum is just this case, which is 26 plus 52 plus 54 plus 56 plus 58 plus 60 plus 62 plus 64, which is equal to 432. And so also we can label this grid with 1, 2, 3, 4, 5, 6, 7, 8. We can label the grid with coordinates in order to be able to properly tell which square is which later on. And so now we can just, without loss of generality, now we can just try to solve it in general, ignoring the max case up here. And so without loss of generality, we can assume that the maximum diagonal is just the one that's already been drawn, this one. The one that's already been highlighted in yellow. I'll draw it in green this time. This diagonal. And so now we can color all the pieces of this board in a chessboard style. And so A and A plus 1 share an edge. And so that means that they are different colors. And so what that also means is that all numbers on the same diagonal have the same parity. And so now we can let m be the smallest. And so now we can let m be the smallest value on a diagonal. And so what that means is that the numbers 1, 2, and minus 1 all lie on the same side of the diagonal. And the reason for this is just because the main diagonal split it into two pieces, and since m is the minimal number on the diagonal, that means that none of the numbers that are smaller than n lie on the diagonal. And so that means that 1 to n minus 1 all lie on the same side of the diagonal. Okay. And so what that means is that m must be at most 29. And the reason for this is just because there are exactly 28 numbers on each half of the diagonal. And this is easily counted. And so if we let m equal 29, if we let m equal 29, then what we get is that the maximal, and so you already know from here that all numbers on the same diagonal have the same parity. And so what that means is that when m is 29, the maximal sum is 29 plus 63 plus 61 plus 59 plus 57 plus 53 plus, no, not 53, 55 plus 53 plus 51. And this sum is equal to 428. But up here, the sum that we found was 432. So this is smaller. And the reason for this is simply because 29 is odd, and so the maximal numbers are all one less than if m had been even. And similarly, if m is equal to 27, then the sum is even smaller. And that means that the sum is also less than 432. So now we have, now up here, this case is just the optimal case when m is equal to 26. So now all we really need to do is let m equal 28 and show that there is some contradiction. And so if m is 28, then the only way that it is larger than this number up here is if the sum is 28 plus 52 plus 54 plus 56 plus 58 plus 60 plus 62 plus 64. And so we already know that 52 to 64 are basically just a bunch of 7 consecutive even numbers. And so what that means is that they must appear consecutively in the diagonal. So like here, either they're this line or they're this line. And so either way, 28 is in a corner. And so without loss of generality, we can assume that this corner is at 1, 1. And so what that means is that 62 and 64 would be at 7, 7, and 8, 8, respectively. And so now we know that 63 shares an edge with both 62 and 64. So what that means is that 63 is either at 7, 8 or 8, 7. And so now, again, without loss of generality, we can assume that 63 is at 8, 7. And if you want to know how to read these coordinates, the first number is going by here, and the second number is the number up here. And so 63 is at 8, 7 here. And so we also know that 61 is next to 60. And so using what we got above, we can see that one is in 7, 8. 7, 8. And so if 1 is in 7, 8, then 1 is above the main diagonal. And so since m is equal to 28, that means that 1 to 27 is all above the main diagonal. And so that covers a total of above main diagonal. And so that covers a total of 27 numbers. And there are a total of 28 numbers above the main diagonal. So what that means is that there is exactly one number that is greater than 28 and is above the main diagonal. And so now we can see that there's two cases for the location of 61. 61 is either in 7, 6 or 6, 7. And so if 61 is in 7, 6, then we can see that we will eventually get stuck at 8, 6. And the reason for this is because 8, 6 must contain a number that is between 2 and 59. But at the same time, we can see that this is impossible. And so now the other case is 6, 7. And so for 6, 7, then we can see that no other numbers are above the main diagonal. And that's because the coordinates that the square that corresponds to 6, 7 is above the main diagonal. And so that means that what that means is that 59, 57, 55, and 53 must be in 6, 5, 5, 4, 4, 3, and 3, 2. Okay. And so we also have that 27 is in 1, 2, and 29 is in 2, 1. And so that means that there is actually no possible location for the number 51, because it shouldn't be in one of these, but both of them have been occupied. And so this is a contradiction. And so what that means is that the maximum number is just equal to 432. So on to level 4. So find the smallest positive integer, find the smallest integer n, such that if any 2016 elements are removed from 1 to n, and one can still find 2016 distinct numbers among the remaining elements with some n. And so in order to do this, first we see that any 2016 elements are taken out. So first we can assume that the taken out elements are just 1, 2, 3, all the way to 2016. And so what that means is that the minimal possible sum among these numbers is 2017 plus 2018 all the way to plus 4032. And we can see that this sum is simply just 1008 times 6049, or 6,097,392. And so that means that n must be at least 6,097,392. And so next up, what we want to do is show that n equals 6,097,392. And so first of all, we can clearly see that the numbers from 1 all the way to 6,097,392 have the number, definitely has numbers from 1 to 6,048. And so now we can pair these numbers up. So 1 and 6,048, 2 and 6,047, all the way to 3,024 and 3,025. And so this is a total of 3,024 pairs. And since we're taking out 2016 numbers, what that means is that of these 3,024 pairs, there are at most 3,024, at least 3,024 minus 2016, which is 1,008 pairs left. And so we can take any subset of 1,008 pairs, 1,008 pairs from the remaining pairs when this is left, and so each pair sums to 6,049. So 1,008 pairs that all add up to 6,049 each has a sum of 1,008 times 6,049, which is equal to 6,097,392. And so now we've shown that n is at least 6,097,392. And we've also given a construction for n equals 6,097,392. And so that means that the minimal n must just be 6,097,392. So thank you for listening.